how do biological patterns form? Why do most animals have bodies with bilateral symmetry? Humans, butterflies, and dragonflies all have left and right sides that are almost the same. Could we walk or run properly if the left leg were much longer than the right leg? We would probably fall after only a few steps. Bilateral symmetry is not just a pleasing shape. It is a survival strategy for moving efficiently and maintaining balance. Everything on Earth, living or non-living, is affected by gravity. Animals and plants grow, move, and live against gravity. As a result, their central body axis aligns with the direction of gravity, and bilateral symmetry naturally develops. Sense organs and limbs, such as the eyes, ears, arms, and legs, are also arranged symmetrically on both sides. This allows animals to perceive their surroundings more accurately and move more quickly. During evolution, individuals with this body structure had a greater advantage in finding food and avoiding danger. As a result, most land animals today have bilateral symmetry. However, not all living things are like this. Living things that drift in water, such as jellyfish and plankton, often have radial symmetry. In water, buoyancy greatly reduces the effect of gravity, and it does not matter much which way the body rotates. As a result, there was no need to distinguish front from back or left from right. The environment plays an important role in determining body shape. Then why do cheetahs have small spots while tigers have stripes? Cows also have spots, but theirs are much larger and thicker. How do these differences form? The person who tried to answer this question mathematically was the British mathematician Alan Turing. Alan Turing is well known for laying the foundation of artificial intelligence, but he also believed that mathematics could explain the patterns of living things. Turing assumed that two types of chemicals in the skin affect pigment formation. He called these chemicals morphogens. If only one chemical exists, it simply diffuses from areas of high concentration to areas of low concentration, so complex patterns cannot form. Even if two chemicals exist, the result is not very different if they do not affect each other at all. But the situation changes completely if the two morphogens promote or inhibit each other's activity while spreading at different rates. In some areas, pigment keeps forming. In other areas, pigment formation is blocked. As a result, patterns such as spots and stripes naturally appear. Turing described this process with differential equations called reaction-diffusion equations. If the activator spreads more slowly than the inhibitor, small spots like those of a cheetah appear. If the two substances spread at similar rates, stripes or maze-like patterns like those of a tiger form. In contrast, if the activator spreads more quickly, large spots or thick stripes like those of a cow can appear. Interestingly, Turing's work did not receive much attention when he first published it. However, as biology and computer simulations advanced, scientists found that real animal patterns form in a way that closely matches his theory. Today, the reaction-diffusion model explains not only animal skin patterns, but also many other biological phenomena, including seashell patterns, leaf arrangement in plants, and the growth of corals and tissues. We often think of mathematics as the study of calculating numbers, but Turing showed that mathematics can even explain the beautiful patterns of life. If invisible mathematical laws lie behind the spots of a cheetah and the stripes of a tiger, what other mathematics might be hidden in the natural world around us?